minds. We learned that standard deviation and variance are statistics that talk about the dispersion of the data. And this information tells us about how spread out the data is. If my data points are close together and very close to the mean, mostly, then I have low standard deviation and low variance. However, if my data points are very spread out and far away from the mean, then I tend to have high standard deviation and high variance values. Another small summary slide here is that we learned that there are certain central tendency statistics, mode, median, and the mean. And for interval ratio data that have both descriptive, ordered, distance, and zero properties, right? So equally distance has an absolute zero value. We can use either or, mean, median, and mode when we are describing our data. In ordinal scales, however, it makes much more sense to use median or the mode because mean usually doesn't mean much. Similarly, with nominal data that only have descriptive properties, only mode makes sense because usually there is no mean or median, or they don't make sense because, as you remember, nominal data, when coded with numbers only reflected some coding and not necessarily their number values. So let's say it was female and male. We did code females as 2, males as 1 in our data. Well, I may be able to calculate a median or a mean for that data. Let's say my mean is 1.2. That doesn't really mean much, right? It doesn't mean female or male 1.2 in my data. Hence, mode, the more popular of the two sexes, will be reflected by the mode, because mode may say, oh, the most popular data point that you have in this variable is female. Then you know that, there are more females than males in your data. Similarly, for dispersion, we learned that there are several different ways to explain and or measure dispersion in my data. I just told you 2 of them: standard deviation, variance. For interval and ratio data, again, standard deviation and or variance make perfect sense, and you are most welcome to use them when explaining your data dispersion or data variability. However, with ordinal data, usually standard deviation cannot be calculated because there's no equal distance between your data points. Therefore, some sort of frequency distribution or cumulative percentage distribution makes much more sense. This distribution just tells you what percent of each data value you have in your data set. Similarly, for nominal data, if I tell you that, 50% of my data points are female, 50% of my data points are male, well, from this frequency distribution that I just told you, you know what your data is composed of and how the dispersion is in your data. Let's review just a few other statistical properties. And as you can note, this is for information only. I'm not going to be asking these in your tests, but this will be useful for our upcoming discussions about the normal distribution and z-scores. So skewness is a measure of the direction of asymmetry in your distribution. If your data is positively skewed, then you have a tail to the right of your curve, just like this one. This is a positively skewed curve that you see here. And then this is the negatively skewed curve right here. Skewed usually messes up with your mean values, so we really don't like skewed data as researchers. And for our analyses, we will assume that every data out there is normally distributed, just like this shape here, symmetric bell-shaped curve, like this one, just to be able to conduct analyses. And then here is kurtosis. Kurtosis does explain how tall your normal curve or your frequency curve is for your data. If your data is leptokurtic, that means there is a lot more data around the mean. Hint, hint, probably a smaller standard deviation. If it's mesokurtic, it's just normal around the mean. And then if it's platykurtic, it is flatter and fatter around the mean. Here we go. If you're ready, let's start talking about the z-score, and we will continue our discussion tomorrow in class. What is a z-score? A z-score measures exactly how many standard deviations above or below the mean a data point is. How you calculate it is, it's your score minus the mean divided by standard deviation. Hint, hint, here is why we're learning standard deviation. So this is your formula with the symbols. Not further ado, let's just do an example on how to calculate a z-score. Our example is that the grades of midterm for Marketing 2300 in spring 2015 at Wayne State has a mean of 82 and a standard deviation of 4. Michael scores 74 on this exam. Find Michael's z-score. If you want to try to attempt this, pause here and try to do the problem yourself. I'm just going to continue. So in order to find a z-score, we take Michael's score 74 and then we subtract the mean grade of the exam here from Michael's score, 74 minus 82, and then we divide it by 4, which is my standard deviation from up above. I could have given you the variance in the question. I could have just not said the standard deviation is 4, but only said your variance is 16, then you would have to calculate the standard deviation from that 16 by taking a square root of that. We just learned about this. But I made your life easier and I just gave you the standard deviation value. So here I go. I do the top math, which gives me a -8. I divide -8 by 4 and I find -2. Michael's exam grade z-score is -2. What does this tell me about Michael's score in plain English? This means that Michael scored 2 standard deviations below the class mean. Why do we care about that? Why do we want to know these z-scores? We usually, as I just mentioned, think that every data out there is normally distributed in a bell-shaped curve like the one you see on your screen. 0 denotes my mean, so this would be my exam grade, and then this is 1 standard deviation lower than the mean, and this denotes 1 standard deviation above the mean. So in nature, we think that most of the data points are going to occur around the mean, just like you see here, as the area under the curve is the fattest, or biggest, largest really, under the mean and around the mean right here. So there is a rule in statistics, which is the 68, 95, 99.7 rule. We assume that 68% of the data points in any normal curve lie within 1 standard deviations from the mean. Similarly, we assume that 95% of the points lies two standard deviations above and below the mean. Similarly with 3. And then we also assume that there is very little data that you can observe that is 3 standard deviations below or 3 standard deviations above the mean. So if you take an example, an average male height for Americans is 5 feet and 10 inches with a standard deviation of 3 inches. So with this information, I can tell you that 68% of the males will be between 5 feet 7 inches and 6 feet 1 inches in the US. This makes sense, right? Similarly, 95% of the people males will lie within 5 feet 4 inches and 6 feet 4 inches brackets here. So most of my population will be measuring around here. And then people who are on the very extreme ends of this scale are going to be lower in percentage in my population. To be very exact, people who are shorter than 5 feet 1 inches are only 0.15% of the population. And then similarly, people who are extremely tall are also 0.15% of the population. So in order to just set this in your minds, LeBron James, for instance, is an extreme value in the population because his height is 6 feet 9 inches. Similarly, Yao Ming is 7 feet 6 inches, and he's also an extreme value in the population. And you can see why these are extreme values, right? Because normal height sizes are usually around here, and LeBron James and Yao Ming are pretty high up there in this normal curve that we're seeing on our screens. So why do we use the z-scores? Well, I just told you guys that when I have a mean of a distribution of anything in the population, most of my data is going to be within 1 standard deviations of the mean, and then there will be some more within 2 standard deviations of the mean. Well, a z-score helps us convert a score from its normal distribution to a standard normal distribution. So when you tell me that someone scored -1 in a test, I know that they scored lower than the mean, and I know I can actually calculate their percentile by just adding up these percentages up here. Similarly for -2. So when I asked you guys about Michael, and we calculated that Michael's z-score was -2, I know, 1, Michael scored lower than the mean. To be exact, Michael scored 2 standard deviations below the mean. We can also learn about the percentile where Michael's score is lying using the z-score table. So let me show you that. Here's my z-score table. I have attached this under resources under the modules. So where does all of that 34%, 68%, 95% that I was just talking to you guys about come from? It all comes from this z-table. Let me show you. Let me just find Michael's z-score here. So Michael's z-score was on the negative side, so it will be on the left side of this table. It was 2.0 and then another 0. this 2.0 tells me the first two digits of my z-score, and then if it was 2.01 or 2.02, I was going to keep looking into the other columns of this table. However, I have 2.00 as his score, so I can see that the area under the curve for this particular z-score is 0.0228. What does that mean? Well, this means that the area on the left of -2 on a standard normal distribution is 0.02228 out of 1. So that means it's 2.28% of the whole population if we think of the whole population as 100%. So Michael scored in the second percentile, which is a really low score. In other words, also only 2% of the class is estimated to score lower than Michael. He is one of the lowest scores in his class. Let me stop this video before I go ahead and talk about confidence intervals.